All right. Last talk of the whole conference. This is very exciting. There's a lot of pressure because all the talks before me have been so good. Okay, so this is a joint work with some of the colleagues at Carnegie Mellon. This work is led by my PhD student, Justin Whitehouse, who is also co-advised by Aditya Wamdes, who's a faculty member at CMU, and also joint work with Ryan Rogers. I will say, this work is 90% or more than 90% of work is done by Justin, who's supposed to give a talk, but he has something else to do this week. So I'm giving a talk. The slides is made by Justin. So most of the credits go to him, or the error comes from me. All right. So as you expect, this talk is about privacy. It's about differential privacy. So you have seen the definition multiple times in this week. It's an algorithmic stability notion that captures the idea of privacy. I will disagree with Mark that I find this to be a very interesting definition. In fact, this Sunday I learned that this is not only the gold standard of data privacy, it's also the golden standard for privacy preserving data analysis. I actually don't know the difference between the two. Apologize for the inside joke. This is coming from the same. Okay, but you have seen this definition multiple times. It's capturing some underlying notion of stability, and the key quantity in this whole definition is really the privacy parameters. How stable the algorithm is captured by the parameters of epsilon and delta, and most of the focus is on epsilon. This is sometimes called a privacy budget, privacy parameter, what have you. Okay. We'll revisit this quantity time and time again. Okay, so what makes differential privacy so appealing is perhaps Aloni gives a nice motivation of this is it's the idea of composition, right? So notions like hey, Anon doesn't really enjoy this composition property, but differential privacy enjoy this compositional reasoning, right? So you oftentimes don't just do one single analysis in isolation and be done with it. Right? You look at the analysis, look at the outcome, you decide to do something else and keep going from time and time again. And so in general, you might run n different algorithms over time. And I apologize, we take little n as the number of algorithms, not number of data points. It's a historical reason we pick that. But in general, you want to analyze how private a sequence of algorithms might be, okay, not just a single algorithm. And luckily, we have done quite a lot of work, starting with the seminal work, Detour, and done. I think almost all the authors are here. That basically think about how the parameter epsilon, also delta, degrade as you compose more and more algorithms, each of which satisfies some epsilon m, delta m privacy. Okay, this expression may look, if this is the first time you see this expression, it may look a little intimidating, but the key takeaway is that if you run n algorithms, each of which roughly have the same privacy parameters, the total privacy budget or privacy cost is scaling only square root of the number of algorithms you run, okay? So this is quite nice, especially like the major building block when you build more sophisticated differential private algorithm that compose many time steps together. Okay, so the square root n is quite nice here. Okay, so many of you have seen that. If you've seen differential privacy, you've seen this many, many times. I think one issue that people don't usually talk about the standard composition is that the choice of algorithm can be chosen adaptively. So the composition inherently is adaptive, right? You look at the output, you decide to choose which algorithm to run later. One caveat in the original or the standard composition is that the set of privacy parameters before you run anything has to be fixed. So if you decide to run some number of algorithms, you sort of have to fix the sequence of parameters you use, the privacy parameters. And most people don't think about this. And in practice, you may want a bit more flexibility. In particular, if you're some data scientist or data analyst, you look at the output from the previous outcome. For example, you want to train this machine learning model. You might think, well, should I use more privacy budget or less privacy budget in the next iteration, or should it be more aggressive or less aggressive, right? So a lot of time there's a strong desire to adaptively choose the privacy parameters as a function of the previous outcomes, right? So you cannot actually decide this whole sequence of privacy parameters ahead of time. Okay, so we want this kind of flexibility. So there are some stuff on this talk. Maybe tomorrow you won't remember most of it. This is something I think may be useful to remember if you decide to use differential privacy. Like a lot of time people want to adaptively choose epsilon, but you have to do that somewhat carefully. Okay, so we're not the first one to think about these issues. How do you actually be fully adaptive? And there's actually a very nice work in earlier days by Rogers, Roth, Mellon, and Madan. But think about how to formulate the idea of fully adaptive composition when your epsilon is being chosen as a function of the previous outputs. There are usually two machinery to think about this. Not necessarily all the machinery for capturing all possible adaptivity. But the simplest one is called privacy filter. That's literally how you think about what a filter looks like. Right? So you want to decide when to basically stop. Right? So you, in this picture, you have a data analyst that keep interacting with the data set. Every choice of epsilon can be adaptive as a function of the previous output, previous answers. But at some point, the filter will tell you, oh, you have to stop here. You cannot run any more algorithms. And at the end of the day, your total interaction will satisfy some target parameter epsilon delta. Okay, so this filter really is just a stopping mechanism. Just look at the sequence of privacy parameter, you stop. Okay. More generally, you can think about privacy odometers, which is arguably a harder task, and here you may not stop ever, right? So you want to maybe keep running your algorithm, keep releasing statistics or models, and at every step along the way, you want to actually provide a tight confidence bound or upper bound on the total amount of cumulative privacy loss exhausted so far. Okay, so from beginning to every time step, and you want to tell basically the analyst how much privacy budget you have used. Okay, so one caveat I won't talk about here. In filter, it still makes sense to talk about the interaction satisfied epsilon delta dp. So epsilon delta is still a parameter fixed ahead of time. We can just tell the filter this is how much budget I'm going to spend. For odometer, it doesn't even make sense to state this thing is epsilon delta dp ahead of time. It's really a running count or running accountant of how much privacy loss you have used so far. Okay. Any question about this? So there's been lots of nice work on this, thinking about this kind of adaptive composition. Luckily, I think there's still space for improvement. I think the filters and odometers constructing the original work, I think the bounds are kind of loose, and they suffer from large constants, and there should be room for improvement, which we did. I want to point out there's another nice work that think about a more specialized version of privacy called Renyi Differential Privacy by Vitaly Feldman and Tiana Zernick. I guess Tiana is here, so she knows everything about this. So that's very nice. So we particularly focus on how do you do filter on Renyi DP. But when you think about using it for composing general epsilon delta mechanism, you might require some kind of conversion cost in between. And they also provide an odometer, I believe, is using building block composing multiple Renyi filters together. which may incur some kind of discretization error. It's not trying to give a privacy loss every time step. Okay. But these are very nice work that sort of opened the door for us to think about our results. So what's our results? First result is basically trying to come up with a tighter, maybe better privacy filter for general classes of epsilon delta DP algorithms. What's nice about this is that basically the rate from the filter basically exactly match the rate that you would get from the advanced composition theorem. So essentially you don't lose anything, even though you're allowing the kind of adaptivity you have. So that's kind of nice. And we also provide not just one privacy odometer. We can actually construct families of privacy odometers by using different tools of super martingale concentration to provide this kind of time uniform bounds on privacy loss. Numerically, we can do much better than the original privacy odometer. Okay, so we have 10 minutes, so I won't go into all the proofs. I want to basically highlight some of the proof idea in the filter prop, maybe leaving some time for a question to be productive. Okay, so I want to mostly think about filter in this talk. So filter again is really, you allow the analyst to adaptively choose the privacy parameters over time as a function of previous outputs. And at some point, you have to just tell the whole interaction to stop. It's really a stopping time mechanism. And at the end of the day, you want to ensure the entire interaction is epsilon delta dp. All right. So I want to quickly, actually, this is the result. This is sort of the bound we get for our privacy filter. Okay. So this is it. If you start composing multiple mechanisms, each of which is epsilon n, delta n, dp, you will stop as soon as this upper bound is hit. So this may look a little familiar because the left-hand side is basically the filter rate for our filter. The right-hand side is what you will see in the advanced composition theorem people tend to use. The only difference is really the ratio e to epsilon minus 1 over e to epsilon plus 1, which is really close to epsilon. So in principle, this is really just closer to epsilon squared, which is like sort of the rate of filter. So numerically, you can't really distinguish them. Right? So the filter and the advanced composition basically exactly match.
Is it e to the epsilon n in the denominator and m in the numerator on the right-hand side?
It's a typo, it's n.
Okay.
Wow, that's a good catch. Okay. So this is just to show this bound is quite good. Basically, filter arguably may be harder to think about, but you can actually match sort of the rate you get for almost as if you pick the epsilon ahead of time. Okay, I want to briefly talk about some challenges in thinking about this proof. The math is complicated, but the idea is simple. Pretty much when you think about privacy proof or this kind of composition proof, the key concept you will think about is the idea of privacy loss, which is really what epsilon is bounding, right? So you want privacy loss to be no more than epsilon at the end of the day. So a privacy loss, this expression takes a little unpacking. It's really saying that if you have an algorithm and you have a pairs of neighboring data sets that differ by one entry, you want to compare the log ratio of the output density. At one algorithm, you use one of the algorithm to output, or versus the other algorithm to output. Okay, so one quick note, maybe if you don't have time to parse it, this is a random variable. That in particular, because A of X is a random variable. A is a random algorithm, so this whole thing is a random variable. If you don't have time to parse it, just think about it as like, how much a pair of algorithm, one on X, the other one on X prime, how much does the log density ratio differ, which is which can depend on the output. Okay. So when you see a definition of epsilon delta differential privacy, it has a strong desire to think about what exactly is epsilon delta dp. And a lot of times when you explain what exactly epsilon delta, you might come up with an explanation that kind of looks like this. So this is sometimes called probabilistic differential privacy. So it means that the privacy loss has a tail bound that looks like, you know, the probability of the privacy loss above epsilon is smaller than delta. Okay, so there's a desire that this should be epsilon delta dp. It feels like, you know, it should just be a clean tail bound on the privacy loss random variable. Unfortunately, they're not the same. Okay, but let's think about probabilistic, you know, dp pdp, which is just like thinking about tail bound on the privacy loss random variable. So here's a general proof sketch, right? So yes, please.
David, can you go back to the left?
Yeah, this one.
Right. So I wonder where the randomness of the PDP comes in.
Where the randomness? Over A. It's a random.
I mean, the definition is.
Sorry. The definition L is here, and here A is random. Yes. X and X prime are sort of fixed over worst case. A is a random algorithm that taking X's. Okay. So here's a attempted approach to prove this thing. So what exactly is filter or even odometer, right? So it's ultimately we're just trying to provide concentration bounds on sum of privacy losses. So we want to bound sum of a bunch of random variables. The variance of these random variables can depend on the previous output. There are tools to handle that. And it's particularly nice if we just analyze this kind of sums of random variables. If each individual algorithm is already probabilistically DP. So what does that mean? Because if each individual algorithm is probabilistic DP, the privacy loss in each round is already given, specified by some very clean tail band, right? Like probably above epsilon is no more than delta. Right? So it's relatively easy to prove a privacy filter if each individual algorithm satisfies probabilistic DP. Okay, so this is, I think, relatively straightforward proof. In the paper, we won't have it today, but so we would like to just use this line of attack because it's relatively simple, except that like what we want to analyze is not just probabilistic DP algorithm, but general epsilon delta algorithm. So in particular, epsilon delta DP actually doesn't equal epsilon delta PDP. Right? So it's an attempted thought. Actually, there's probabilistic DP is actually a stronger concept. Having a tail bound on privacy loss immediately implies epsilon delta DP, but not the other way. So actually, you can convert it back, but in general, you sort of pay for a factor 2 in these parameters. So paying for a factor 2 could work. It could make this work, but it's not nice. Immediately, your composition just double, like the loss just double. How much time do I have? Ooh. All right. So we want to avoid paying for the factor 2, and one very nice tool for thinking through the proof is thinking through a variation of this mechanism called randomized response. It's actually not the exact randomized response you think about in the original Warner method. Sometimes this is called the leaky randomized response because in addition to the bit flipping mechanism, you actually have additional delta probability to basically reveal which data set you're on. So in this case, the leaky randomized response takes in a bit B that indicate whether it's X or X prime. In some cases, we will respond which data set it is with randomized response, but with small delta probability, we will exactly tell you which data set was the input. So this actually satisfies epsilon delta probabilistic DP. So as an implication, they also satisfy epsilon delta DP. Why is this useful? Why should I talk about this at all? What's nice about this is that for any epsilon delta DP mechanism, you can actually just think of it as a randomized post-processing. When you're analyzing the privacy loss, you can just think of it as a randomized post-processing of the leaky randomized response. So no matter how complicated the algorithm is, it suffices to sort of only think about this leaky randomized response, which only have like four outputs. Right? Okay, so this leads to sort of a slightly detour that can still allow us to use the same proof, right? So we can start with algorithm that's epsilon delta DP, but we just need to analyze it as a sequence of leaky randomized response. Once we do that, there's like nice tools to think about how to add up these like random variables with nice tail bounds because they satisfy PDP. And once we do that, we can actually post-process it to actually get back to what the original sequence algorithms look like to satisfy epsilon delta DP. So you get around this conversion factor too. And don't have time, but I want to quickly flash the result of privacy odometers. We have some improvement over the original privacy odometer. So this is the x-axis here is sum of the epsilon squared, one thing we realized when we work on this paper is that when you think about some of these composition results, sum of epsilon squared is actually the right quantity to think about because it's sort of the intrinsic time of privacy composition, not the number of algorithms you compose. And you can actually draw out these kind of privacy loss bound as a function of this intrinsic time. And the red one is actually the original odometer. In general, odometer works give a tighter bound than the original. And I won't show you the bound. Actually, I will show you the bound really quick. It's ugly, but numerically, it's quite nice. And I think there are some interesting future directions here. For example, can you actually handle different notions of variation of DP, like Gaussian DP, FDP? One empirical question, or maybe somewhat interesting theoretical question, is whether you can use this kind of adaptive epsilon setting or these tools of filter and odometer to actually improve some iterative algorithms like MWAM or DPSGD. And this kind of ideas of filter and odometer interact with things like concurrent composition, what are the complexity there? With that, I'm going to conclude my talk and maybe the conference.